So
Okay,
am I
okay,
audible?
okay. We are able to see the slides, and so let me introduce you Sundeep Singh. He is presenting a work dealing with cardiac tissue deformation and the efficacy of radiofrequency ablation. And his work is made a collaboration with Professor Melinik from the Basque Center for Applied Mathematics, Bilbao, Spain. So the stage is yours,
Okay.
please.
Yeah. So thank you for the opportunity. So I am going to present our research related to modeling of coupled mechanical, electrical, and thermal effects during the cardiac ablation process. Yeah. So this is brief overview of my presentation. I will start with clinical relevance of the proposed problem, then discuss in brief about the theory behind radiofrequency ablative procedures, and then elaborate the coupled electrothermal mechanical models that we have developed for the cardiac ablation, then showcase some of the results obtained from those models before concluding my presentation. Yeah, so basically arrhythmias are the most common heart-related disease that are related to abnormal heart rhythm. So during arrhythmia, heart can beat either too slow or too fast or with irregular rhythm. And the major symptoms are, like the common symptoms are heart palpitation, shortness of breath, and low energy. If remained untreated for a longer duration of time, it could even result to worse situations such as stroke. And like radiofrequency assisted cardiac ablation has already proved to be a safe and effective treatment modality for treating different types of cardiac arrhythmias. So during this procedure, the culprit region, the region from which arrhythmia is being propagated or generated is either locally heated and destroyed by applying RF waves in that particular region. Yeah, so this is a schematic of RFA procedure. During RFA, an electrode is inserted percutaneously inside the target tissue with the aid of image guidance modality that can be CT scan, MRI, or ultrasound. And once positioned, a high frequency alternate current in the range of 450 to 550 kilohertz is delivered from the RF generator to this electrode. And as the high frequency alternate current interacts with the biological tissue, frictional or joule heating is induced due to the agitations of ions such as sodium, potassium, and chlorine present inside the body to follow the polarity of high frequency alternate current. Ground pads are placed at patient back or thigh so as to complete the electric circuit. So by virtue of this agitation, two zones of heating are produced. So first one is direct heating zone, that is just few away from the active tip of the electrode, whereby heat is accumulated due to direct interaction between ions and electrons. And the heat accumulated in this region is further propagated to more peripheral areas by the virtue of thermal conduction. Yeah, so the goal during RFA is to attain temperature the temperature greater than 50 degrees Celsius that will basically lead to protein denaturation, damage to mitochondrial dysfunction, halt in certain enzyme function, and cell membrane collapse. So the maximum temperature during this procedure should not exceed 100 degrees Celsius because it will lead to tissue charring and water vaporization that will basically lead to drastic decline in electrical and thermal conductivities of the tissue and will further result in poor image resolution. So one of the most commonly used electrode during cardiac ablation is a saline irrigated open electrode. So whereby the saline is infused from these holes that are in the electrode so as to minimize this effect of charring within the tissue. Yeah, so this computational modeling and simulation provide a powerful tool for a priori prediction of the treatment outcome during cardiac ablation procedure. So during like this, they could also be used for providing the effect of different extrinsic and intrinsic factors that could affect the efficacy of cardiac ablation. Several studies have been reported in the past several decades on modeling of cardiac ablation, but in most of the studies, the effect of tissue deformation has been neglected, and those are basically based on only the electrical and thermal parameters. So in this particular study, we have coupled the mechanical effect as well, whereby we will be trying to couple the effect of the tissue deformation within the cardiac tissue due to the non-uniform heating during this cardiac ablation procedure. Yeah. So basically, during RFA, electromagnetic energy is used to heat the biological tissue, and the interaction and propagation effect of this electromagnetic waves are well described by classical Maxwell equation. But in the frequency range that is being used during RFA, that is 450 to 500 kilohertz, the wavelength of electromagnetic field is several orders of magnitude higher as compared to the size of active electrode. So thereby, a quasi-static approximation can be used without much loss of accuracy. So by quasi-static approximation, we means that electrical and magnetic field effect will be decoupled and the propagation effects will be negligible. So just by solving this generalized Laplace equation, what one could easily solve for the electric field distribution within the tissue during this RFA procedure. And the volumetric heat generation during this heating is nothing but the product of current density and electric field intensity that can be further simplified to this particular expression, where sigma is the electrical conductivity of the tissue and E is the electric field intensity. Yeah. So for solving the temperature distribution within the cardiac tissue during this cardiac ablation procedure, we have used the well-known Penz bioheat equation that is based on Fourier law of heat conduction. Here, this left-hand side denotes the transient effect. So this is the heat conduction term. This is the blood perfusion term that will be sort of heat sink effect caused by the microvascular perfusion within the cardiac tissue. M is the metabolism source term, and QP is the electric source term that will be coupled from the expression I just showcased in the previous slide. Yeah. So further, the ablation volume has been quantified by the isotherm of 50 degrees Celsius that basically represents the region of the tissue where the temperature is greater than or equal to 50 degrees Celsius. So that region will be assumed to be coagulated post cardiac ablation procedure. Yeah. So we have modeled this cardiac tissue as a hyperelastic material, whereby Cauchy stress tensor are given by this particular expression, and we have used a two-parameter Monet-Rivlin model for describing the strain energy function that will be coupled with this equation, and the thermal expansion of hyperelastic myocardial tissue is given by this expression, where epsilon is the thermal expansion strain and alpha is the thermal coefficient. So all these expression will be going to this standard thermoelastic wave equation for non-rigid mechanics. And F is the body force that has been neglected, that has been assumed to be zero in this particular study. Yeah. So we have assumed both temperature dependent thermal and electrical conductivities. So this is the expression for thermal conductivity, whereby there is a linear increase of electrical conductivity up to 100 degrees Celsius, and then it stabilizes. The electrical conductivity increases by 2% till 100 degrees Celsius, and it abruptly declined due to this water vaporization and charring that occurs at 100 degrees Celsius close to the active tip of the electrode. And after that, it becomes a very low value. Again, we have modeled this blood perfusion as a temperature dependent piecewise parameter, where there will be a constant value of blood perfusion rate below 50 degrees Celsius, where we have assumed that this as a critical threshold where the ablation volume has been quantified, and it will be zero beyond this temperature due to damage to all the microvasculature that is present within the cardiac tissue. Yeah, so this is the computational domain. Is like this is the heart. Normally, arrhythmias is like cardiac ablation is used for treating arrhythmias in the right and left atrium. So this is the culprit tissue. So instead of modeling the entire this complex geometry, we have focused only on the limited domain model, where we will be modeling only this cardiac tissue. This is the cardiac tissue. This is the catheter that has been inserted. This is the catheter, and this is the blood domain, blood chamber. So we are going to model only this simplified domain here. And further, to reduce the computational cost, we have assumed the axisymmetry model, this model. This is the electrode, and this is the insulated part. This is the cardiac chamber where the blood flow will be there, and this is the cardiac tissue. So yeah, I will now discuss initial and boundary conditions. The initial voltage of the entire model has been assumed to be zero, and this is the active part of the electrode. We have modeled a constant power cardiac ablation. So a constant voltage will be applied to this particular zone, and different values of blood flow rate has been assumed. Like a high blood flow rate has been assumed to be 8 centimeter per second, and low blood flow rate is 3.5 centimeter per second. And again, to simplify the complexity, we have reduced this. Instead of solving the full-fledged fluid flow model, we have assumed convective boundary conditions here. Like this is the convective boundary condition between the blood and the cardiac tissue, and the convective boundary condition between the electrode and the blood, so as to reduce those computational costs. And since our motive is to quantify the ablation zone within this cardiac tissue, and we are not at all interested with the temperature that will be increased in this blood chamber. Yeah. So so apart from this, during these procedure, normally the applied force is like the force is applied at the top surface of the electrode that leads to a certain insertion depth within the cardiac tissue. So we have considered this force to be in the range of 10 grams to 40 grams, and that basically results in this deformation of 0.5 to 2 mm within this cardiac tissue. So in most of the studies, those are available in literature, this deformation has not been accounted. This electrode insertion has been assumed to be a sharp insertion within the electrode. But in this study, we have accounted for the deformation that will be induced by inserting this electrode within the cardiac tissue. Yeah, so this is the dispersive electrode where we have modeled a ground condition by specifying a 0-volt condition, and the entire initial temperature of this cardiac tissue has been considered to be 37 degrees Celsius. That is similar to that of core body temperature. Yeah, so these are the material properties that are basically taken from literature. Yeah. So these are the displacement field distribution and deformation at the electrode interface. So as you can see, so these are for different values. Means like if the insertion depth is means like we have we have defined a prescribed displacement at this electrode in vertically downward direction, and these are 0.5, 1, 1.5, and 2, and these are for the range between 10 to 40 grams of contact force that has been assumed to be safe and reliable in the clinical trials of cardiac ablation. So as you can see, like if I am increasing the insertion depth from 0.5 to 2, so you can see a slight deviation of the tissue. So this deviation could possibly result in overestimation of the ablation volume if we assume a sharp insertion of this electrode instead of accounting for this deviation. So these are the line plot of the same figure that I have presented earlier. So as you can see, this will be the tissue without deformation, and these are the deformation for different values of insertion depth. So as you can see, there is a pronounced effect of this electrode insertion on the tissue deformation, and basically this region, this particular region would be completely filled by blood, and it could act as a heat sink effect, whereby the heat supplied will be basically taken away from this blood and won't be going within the cardiac tissue. So this could result in overestimation of the ablation volume if we assume just a sharp insertion, whereby the electrode is inserted, but there is no deformation at all. Yeah, so these are the von Mises stresses distribution for different value of insertion depth. So as you can see, like the maximum value goes to around 40 kilopascal for 2 mm insertion depth. Yeah, so this is a comparative analysis of temperature distribution assumed with sharp insertion on left side, and this is by assuming a deformed surface due to the insertion of electrode. So as you can see, there is a significant deviation, and this deviation increases as we increase the insertion depth for this particular case, and these results are for high blood flow condition, and for this particular case the deviation has been found to be close to 20%. And again, the similar results have been obtained for low blood flow rate condition. And again, you can see like for this condition, the deviation is found to be close to 25%. So that means that sharp insertion basically overestimate the ablation volume as compared to when there is certain deformation at the surface. Apart from this, we have coupled, we have fully coupled electrothermomechanical model. So we have also accounted for the thermal stresses that are induced within the cardiac tissue due to this non-uniform heating. So yeah, so these are the results of von Mises stress distribution due to the non-uniform heating. So as you can see, there is a significant portion of tissue that has been deformed due to this. Like these are basically because of this thermal stresses that are induced within the tissue. And this means like the particular column reflect 0.5, this is for 1, this is for 1.5, and this is for 2, and this is for high blood flow condition, and the column 2 is for low blood flow condition. So as you can see, the amount of thermal stresses increases with the increase of insertion depth. Yeah. So yeah, so I would like to conclude that we have developed a fully coupled thermo-electromechanical model of cardiac ablation for more accurate prediction of the treatment outcomes that would basically lead to the slight deviation between experimental and numerically predicted values, and it could be extended by incorporating the complex geometries and the actual blood flow models and all those stuff. A comparative analysis has been conducted to evaluate the impact of tissue deformation for both low as well as high blood flow conditions. Our findings suggest that the ablation volume attained during cardiac ablation is significantly dependent on the contact force as well as the blood flow rate. So the thermal stress distribution have also been presented, and we expect the advancement and extension of the developed model could significantly assist the clinician in better optimizing the thermal dosage for enabling safe and reliable cardiac ablative procedure. So these are the selected references, and yeah, thank you for your attention.
Yeah, thank you very much, Sundeep, for the very interesting talk, full of insight, comment, and presenting us this very sophisticated model. The stage is open for questions and comments. Let me see, I see a hand raised by Professor Dussel. Please turn on the mic.
Yes, thank you. I'm the first asking the question again. Sorry about that. But I enjoyed your talk. It's a major step forward to take into account the deformation. But you still neglect the saline solution, the irrigated tip. And do you have arguments why you think you can neglect that, or is it the next step to
basically
include?
that's the next step. What we have done is instead of modeling that saline inflow through those infusion holes, what we have done is specified a constant value of temperature here. Again, this is a rough estimation. So basically the overall idea was to compare the ablation volume quantified, neglecting that deformation part. So as we have seen that like there is significant deviation, like overestimation of the result if we assume a sharp insertion of that electrode in this procedure.
Yes, I see. You just fixed the temperature of the metal.
Yeah. So for this,
sense.
so assuming that there might be some saline infusion, so we have kept that temperature of 45 degrees Celsius maintained throughout the 60-second cardiac ablation procedure.
Thank you.
Yeah.
Thank you, Professor Dussel. We have another question from Massimiliano Leoni. So please, Massimiliano, can you turn on your mic?
Done. Can you hear me?
Yes.
Hi. I wanted to ask about the results that you presented. Are they published already?
A part of this is under consideration in a journal.
Okay. I'm asking because you said that there is no study that took into account the elastic deformation of the tissue.
No, elastic deformation plus coupled model. Elastic deformation are there. There are one or two studies, like there is a group from Bilbao that has published this elastic deformation, considering elastic model, like cardiac tissue has been modeled as a linearly elastic material. So
okay, I'm aware of that because I'm one of the co-authors of the study that you just mentioned.
Okay. Yeah, that's good.
Right. So this takes me to the actual question that I wanted to ask. How do you, how much power do you dissipate in the tissue? Because that's one of the most critical issues that we had in our paper.
Yeah, it is close to 20 watt. Again, on a lower side, we want to extend this, but still it is on a lower side. Yeah, it's 20 watt, close to 20 watt.
Okay. And again, how did you pick this number?
It is from the available studies, like the numerical studies available in literature.
Okay.